So this is where we left off, and 78 was one of the exercises, finding binary code of 78. Anybody has that answer for me?
Yeah, I got 1001110.
That is correct. Did everybody else get the same?
Yeah.
Yes.
Okay, all right, one more student confirmed it. So that is correct answer. And if anybody, I don't think you have, anybody has a question, you should have done it already. But let me ask the question. Is there anyone who wants me to go over that problem? 78. All right, good. Okay, so that's how you find the binary code. You have to write it as a sum of powers of 2, um, and then read the coefficients of the sum of powers, of all the powers. Um, Now, how do we go backwards? If I ask you to find the decimal code of the binary number, how do we do that? So let's do that for this exercise itself. This one, you found this as answer for the 78. So let's see, let's go backwards now. If I give you this binary code and ask you to find the decimal equivalent of this number, then you would write this. This 0 means 0 is the coefficient of 2 to the 0. This 1 means it's the coefficient of 2 to the 1. So you write those things. 1 times 2 to the 2 plus 1 times 2 to the 3 plus 0 times 2 to the 4, 0 times 2 to the 5, they'll be 0, so I don't have to write them. 1 times 2 to the 6, so 1 times 2 to the 6. I write that, and then I need to simplify all these. So 2 to the 6 would be equal to
64.
64, right? 64, 2 to the 3 is 8, and 2 to the 2 is 4, 2 to the 1 is 2, and this is 0. 0 times 2 to the 0. So 64 plus 8 is 72, plus 6, plus 4 is 76, plus 2 is 78. So the sum of all this is equal to 78. So 78 is the decimal equivalent of the binary number 10011101110. So that's how you go backwards. For any binary coded number, we can find decimal equivalent. So let's move on now. The shortcut to binary code. How do we find the binary? Is there a shortcut method? Do we have to always write this long expression? No, actually, there is a shorter method. I'm going to give you that. The reason why I asked you to write this, use this longer method before, was that you understand the binary coding better when you do it this way, the long way. So the shortcut method is as follows. You just repeat by the base. The base of this system is 2, right? You repeatedly divide by the 2. That's the idea. So I'm going to do the 37 first by the shortcut method. 37, you divide by 2. I'm doing it on the board here. 2 divides 37 into 16. 18, that is. And the remainder is 1. 2 times 18 is 36, so remainder 1. Write the remainder on the side. So you keep dividing and write the remainder on the side. 2 goes into 18 9 times, but 2 times 9 is 18, so there's no remainder. So you still have to write the 0 as the remainder. Divide by 2 again, 4, remainder is 1. 2 times 4 is 8, so remainder is 1. 2 goes into 4 2 times with the remainder of 0. You have to keep going until you get something less than 2. So less than 2 will be 1. So I had to divide again. Divide by 2, that's 1 and 0 remainder. You have to write the remainder at every step. This last remainder is the one that students often miss. You must write the remainder at every step. Okay, after you do that, you read these remainders starting from this 1. Read all these from bottom up. In other words, this bottom 1 is the first digit. 1 0 0 1 0 1 1 0 0 1 0 1. Bottom up. This is your binary code. So the remainders, including the last one you have, starting here, read the remainders, bottom up, that's your binary code. Okay, so this method is much faster and you would find it easier to use. So let me see if you can find the binary code of 86 by using this method. Go ahead.
Professor, can you explain this method one more time? Because
Okay.
I didn't really understand it.
Others can go ahead with the 86. The students who need explanation second time, I'm going to do it second time. So let me erase this and work this all over again. Okay. So start with the 37 and divide it by 2. 2 goes into 3 one times, remainder 1, so 17. 2 goes into 17 8 times, so 18. 2 times 18 is 36, so there's a remainder of 1. You can do this in the calculator if you like. Divide the 37 by 2, you'll get 18 point something. Just drop the decimal part, 18 is your answer. And 18 times 2 is 36, so remainder is 1. Remainder will be 100. Now 18 is an even number, so therefore when I divide by 2, there will be no remainder. So 2 times 9 will be 18. The remainder is 0. Right? Are you with me so far?
Yes.
Okay. Divide by 2 again. You have to keep going until you get a number less than 2, which will be 1. So divide by 2. 2 goes into 9 4 times, but 4 times 2 is 8, so remainder is 1. Divide by 2 again. 2 goes to 4 2 times, but remainder is 0. 2 times 2 is 4, so remainder is 0. Divide by 2 again. 2 goes into 2 one time, and the remainder is 0. So now these are these digits starting at this 1. These remainders will make up your code. So 1 0 0. This 1 0 0 1 0 1. Okay.
Thank you.
Okay, so anybody has the code for 86?
So can I answer that?
Yep, go ahead.
I got 0 1 1 0 1 0.
Okay. All right, I'm going to quickly find it on the side. 86 divide by 2, 43, remainder 0. 2 divides 43 into 21, remainder 1. 2 divides 21 into 10, remainder 1. 2 divides 10 into 5, remainder 0. 2 times 2 is 4, remainder 1. 1 0. So 1 0 1 0 1 1 0. You missed a 1 here.
That's what I said.
Oh, you said that? All right, maybe I wrote it wrong. Okay, anyway, the code is 1 0 1 0 1 1 0, starting at bottom. 1 0 1 0 1 1 0. Okay. Okay. Now I just we need to go backwards. If I give you any decimal number, you have to be able to find the binary. If I give you any binary number, you have to be able to find the decimal equivalent. So let's start by, let me use this as example. 1 0 0 1 0 1. We know that that is the binary code of 37, right? So let's see if we can find. Hold on, somebody just came in. let me erase. Okay, so if this decimal, the binary code is given 100 100 101, find the decimal equivalent. So what you need to do is, you know that this last one corresponds to 2 to the 0. So it's 1 times 2 to the 0. The previous 0 corresponds to 2 to the 1. So since it is 0 times 2 to the 1, it will be 0, so I don't have to write it. So that's 2 to the 1. This is 2 to the 2. So 1 times 2 to the 2. And this corresponds to 2 to the 3, 2 to the 4, 2 to the 5. This one is 2 to the 5. 1 times 2 to the 5. I just didn't write the 0 times because they're all equal to 0. And now I have to evaluate the entire expression. This is equal to 32. And this is equal to 4. This is 1. And add them up, I'm getting 37. So 37 is the decimal equivalent. So you basically write that expression that corresponds to that binary coding and then simplify it. Okay, so let me see if you can find the decimal equivalent of this binary number, 110101. Go ahead and find it. Okay, anybody has an answer?
I got 53.
Yeah, me too.
Okay, very good. 53 is right. Anybody needs explanation?
Yeah, could you actually do it like on that whiteboard that you have?
Okay. I have 110101. So this last one corresponds to 2 to the 0. So I have 1 times 2 to the 0 plus this corresponds to 2 to the 1. I don't have to write that. This is 2 to the 2. So 1 times 2 to the 2 plus 2 to the 3. I don't have to write that. That's a 0. 2 to the 4 and 5. 2 to the 4, 2 to the 5. Okay, 2 to the 5 is 32. 2 to the 4 is 16. 2 to the 2 is 4. This is 1. Just add them up.
Got it.
Okay. All right. So let's proceed now. So the ASCII code, the coding system, what we call machine language, uses this coding system, which is also known as ASCII coding system, in which all the characters have a code in using ones and zeros. So every character has an 8 ones and zeros in their codes. So we call those ones and zeros bits. So there are 8 bits in every code. And this was designed by the IBM company. This coding system was designed by IBM company. IBM company was the very first company to build computers. So they developed basic details of the language. So they developed this coding system. in which they specified, this is the code for A, and this is the code for B, and this is the code for C, and so on. So those codes, all of those together is called the ASCII language. The actual name is American Standard Code for Information Interchange. This was the original name. It is abbreviated as by the first letters of each word, ASCII, and we read it as ASCII. In this coding system, the letters and symbols, all the symbols that we use, like semicolon, colon, period, all of them have a code. And for the numbers, the ASCII code will be binary code for the numbers. For the letters and symbols, the codes have been already designed by IBM. So we will be using the ASCII codes when we store numbers or letters in the memory of the computer. So ASCII code of character A is 010001. This is the ASCII code. And if you actually find the decimal equivalent of this code, or if you find ASCII binary code of 65, that turns out to be the same as this, or the decimal equivalent of this code is 65. In other words, the character A and the number 65 have the same code. So what does that mean? That means if I store the number, the letter A in the memory, the uppercase letter A in the memory, then this code will be stored 01000001. If I store number 65, the same code is stored in the memory. So how does the system know whether a number or a character has been stored, whether I have stored letter A or 65? How does it know? Well, it doesn't. System doesn't know what you stored. It's the programmer who has to keep track of what he or she stored in there and take it out in that same form, or even you can take it out in the converted form. 65 converted to alphabet will be character A. A converted to number will be 65. So system doesn't know the difference. You have to know the difference. And even if you just add two characters, A and B together, system will go ahead and do the addition, because as far as the system is concerned, there's no difference between letters and numbers. They're all the same. So the programmer has to keep track of what was stored and what you want to do with it, and all that is up to you. Okay, so move on. So here are the codes, some of the codes. The entire list of codes are there in the back of your book in the appendix, but you don't really need to read them. But it is helpful to know that the uppercase letter A corresponds to 65, uppercase B corresponds to 66, uppercase C corresponds to 67, and so on. So in a program, if you actually compare these characters, you're actually comparing these numbers. So therefore, character A and B, how do they compare? A is smaller than B, because A is 65, B is 66. So characters can be compared if you need to. In fact, if you want to put them in alphabetical order, you do compare them by using inequalities. Later, when you actually start programming, you will understand those a little more. So the alphabets are in order. The 65 for A, 66 for B, and 67 for C, they designed it that way so that they are in order. Lowercase a corresponds to 97, lowercase z corresponds to 122. So knowing this interval will be helpful. 65 to 90 will be uppercase A through Z, and 97 to 122 will be lowercase a to Z. So what is between 90 and 97? Some other codings, some other symbols are there. We don't care what they are. But these are the codings of the alphabets. And this range is actually needed to answer some of your questions, homework questions, test questions. So therefore, this range will be given to you in the test. Uppercase letters A through Z correspond to 65 to 90. Lowercase alphabet A to Z correspond to 97 to 122. That information will be given to you in the test because you need it to answer some questions. So let's proceed to understand a little more about character data in the computer memory. I said earlier, every character is coded using ones and zeros because only ones and zeros can be stored in the computer memory. So let me elaborate on that. Why ones and zeros? Because a computer is a machine just like a VCR or DVD player, and it can only recognize one thing. When there is electricity going through it, it'll be powered up and ready to go. And it can recognize the electricity, the power. So machines can recognize power. So the scientists, mathematicians went a little bit deeper into that and realized that machines can actually recognize when there is power in the circuits. In a circuit, there is a power, there is electricity going through it, the machine can recognize that. And so they thought, okay, then that means machine can recognize electric circuit when it is on, then it can recognize off, right? If it recognizes on, that means when there is no electricity, it recognizes that as off. So that means there are two things the machine can understand. So if machine can understand two things, then all we have to do is represent everything using two things, then we can represent them in the machine. That's the idea that led to the computers. Represent everything using two things, then you can represent them inside machines. So they decided to go ahead and pursue that idea, and then it went into serious researches and for a long time, and eventually they decided they can build a machine that can understand everything we do in our life by representing everything using on and off. So you take a circuit and have it turned on, there will be power in it, and have another circuit turned off, then there will be no power in it. So the machine can recognize when there is power in one circuit and no power in the other circuit and things like that. So by creating a pattern of on and off, you can make a whole a set of circuits turned on and off to represent a character inside the memory. That's the idea that led to the computer. So what we do is we turn circuits on and off inside the RAM, the memory, in a pattern. So the pattern would be, for example, if the letter B is to be stored in the memory, letter B has this code right here. So to store that, you take 8 circuits of the memory and turn them on and off according to this. Every 1 will be represented by a circuit turned on. Every 0 will be represented by a circuit turned off. So have a pattern of several circuits turned on and off. So I'm going to show you on the board now. This is confusing picture. I need to change that picture. If I ask you to do this in a homework, don't use that kind of picture. Use this. A circuit will be, the first circuit is going to be off. So you show that this way. This is off. And second circuit is on, that'll be closed circuit. And next one is off. You show that this way. Off, 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 4 off, and then on, and then off. So this is 8 circuits that represent letter B. So letter B is represented right here in the memory. So this pattern of on and off, the machine can recognize. There is electricity in where, some of them have electricity, some of them don't. So the pattern can be now recognized as letter B. So this 8 circuits together, all these 8 circuits together is called 1 byte of memory. The amount of memory needed to store 1 character is called 1 byte. Memory needed to store 1 character is what we call 1 byte. So physically, 1 byte of memory has 8 circuits. So what is there physically in the memory? Circuits. That's what you have. So one character takes this 8 circuits means if I store another character in the memory, another 8 circuits have to be used to represent that. So if you type a term paper, you can imagine how many bytes of memory is needed. So memory has to be huge. You need millions and millions of circuits inside the memory. And that's exactly what you have in the memory. A memory chip, what we call memory chip, is a silicon material, chip made with silicon material. It's a piece of silicon, basically, with millions of tiny circuits buried in it. So the physical component inside a memory chip is circuits. That's what that is. There's nothing else. There's no machinery, nothing inside the memory chip. Loops, tiny loops. They're so tiny that you can't see it. That's how they brought the computers down to small size, by making these loops tiny. The loops don't have to be big, so they made them really small, and you cannot see them, but that's what they are. So in the memory, what you have is bytes of memory all together inside the chip. So every byte is good for one character data. But when you store numbers, you may have to use more than one byte depending on the size of the number. But characters use only one byte, each character. So the 1 byte of memory consists of 8 circuits. We call it 8 bits because they are used for 8 ones and zeros. The ones and zeros are the ones we call bits. So therefore, it is a correct statement to say 1 byte is equal to 8 bits. And if I ask you the question, what is physically there in the memory chip, you would have, your answer will be circuits. They're all circuits. So this is 1 byte of memory right here in this picture that shows 8 loops. That's what you have in 1 byte of memory. So the memory chip that we have inside the computer has millions of circuits in one little chip. And so when people say they upgrade the memory, they buy a memory chip and plug it into the motherboard. And when you do that, you are expanding the memory by another memory chip. Basically, that's what it is. So every time we store a character, we are turning circuits on and off according to the ASCII code of that. So we can store the character in a variety of different ways. After we start writing computer program, you will see how to store a character by writing a statement in the program. But you're also storing character by typing on the keyboard. For example, let's say you run a word processor. After you run the word processor, you start typing your term paper. So every time you hit a key, what is going on? When you hit a key, like character A key, is there A going on through the wire? No. The job of the character A on the keyboard is to set the memory memory so the 8 circuits turn on and off according to the ASCII code of that character. So if you type the B, when you type B on the keyboard, you are doing this to 1 byte of memory. You're setting them on and off. That's the job of that key, B, to turn those circuits on and off according to the ASCII code of that character. So every key on the keyboard is programmed to do this on and off setting to 1 byte of memory. So as you proceed to type the term paper, each character you type will take up 8 bits of memory, or 1 byte of memory, and circuits are turning on and off according to the code. So that's what's going on in the memory. So as long as so you type everything and then they're showing up on the screen, but what is showing up on the screen is what is in the memory. So you're actually storing in the memory, and the memory is being displayed on the screen. So the screen is showing what is in the memory. So after getting it on the screen, if you edit it, you're only editing the memory version of the file, whatever your term paper or whatever. Anything in the memory stays there only as long as the computer is on, because it needs power. You can see that these circuits have to be turned on and off. So if you turn the power off, all the circuits are off and memory is erased. So you have nothing saved there. So after you type and you edit, you manipulate, everything is being done to the memory copy. And only when you select save, you're putting a copy of that into a permanent storage. What goes into the permanent storage will be staying permanent, but what is in the memory will be erased. So what you're editing is the version of the file that is in the memory. That's what you're editing. Only when you're saving a copy of it on the hard disk or external storage. Okay, so the memory, the memory is erased when the computer is turned off, and you can now understand why the memory is turned off. Memory is completely cleaned when the computer is turned off, because memory needs power to hold the data. So that's the reason why every time you turn the computer on, the booting process has to go on again, because everything in the memory is erased. The computer needs the operating system in the memory to function. So therefore, every time you turn the computer on, it has to copy the operating system from the hard disk to the memory before it can function. So it has to do the booting process, which is copying operating system all over again every time you turn the computer on. So this memory works by the power, but the external storage can hold information permanently, and they don't get erased under any circumstances. So how do they do that? Because these external devices, storage devices, do not use this power storage technology. The power storage method is needed only for the RAM. So the external devices use different technologies. So all you need is two different things. If you can find a way to represent two different things, everything is coded using everything that we call digital is coded using zeros and ones. So to store it anywhere, you only need to have a way of representing 0 and 1 in two different ways. So the hard disk, there is a physical disk. The technology on the hard disk is exactly the same as the technology on the music records. Basically, what you have on the surface is millions of tiny magnets. Magnets have a directions, there is North Pole and South Pole for the magnet. So therefore, by pointing the magnet in certain way, you represent 1. By pointing it the other way, you represent 0. So when you're recording something, you're turning these magnets, when you're recording anything, data or whatever you're storing, you're turning these magnets in different directions to represent zeros and ones. So one character will be represented by 8 magnets turned in opposite directions according to the code. And all the characters can be stored that way. So that's the technology on those on the hard disk or diskette. All those use same technology. Now CD uses a very simple idea. It's a plastic disk, and you represent 0 by a hole, punching a hole on it, and you represent 1 by no hole. So hole, no hole pattern will be used to represent the ASCII code of the character. So when you are storing characters in the CD, when you're storing data in the CD, you are punching holes. So you're punching holes using laser light. Laser means, laser is exactly the same as concentrated light. That's what it is. You can use that concentrated light to burn anything. And you're burning holes in the CD by using concentrated light, which is what we call laser. So the hole, no hole pattern will be permanent, and you cannot erase it. And that's why CD cannot be erased. And that's why CD cannot be reused. Once you punch those holes, they're permanent. So that's why we say we're burning a disk, because if you're physically burning it, you're burning holes in it when you're storing something on a disk, and it cannot be reused. That data is permanent. Each one of these device uses a different technology. They don't need power to hold the information. Only the computer memory needs power. And that's the only way to represent that, because computer can only understand power, no power setup. The pattern of power, no power can be understood by a computer. Nothing else can be understood by the system. Now we need larger measurements for our memory because, you know, very large memory is used in computers. So we don't want to measure distance between two cities by inches. We want other units. So that's why they created these larger units. A kilobyte is same as 1,000 bytes. The accurate number is 1,024, but we can just use 1,000. It's very commonly used. And so the 24 is not a big deal. 1,000 is so much easier to use. That everybody uses that 1,000 as the number. So we don't use 1,024, just use 1,000. Some students use 1,024 to answer the questions in the homework, and that complicates matters. Don't do that. Use 1,000. So let me erase the board. One kilobyte equal to 1,000 bytes, and 1 megabyte equal to 1,000 kilobytes. So let's write that down. 1 megabyte equal to 1,000. So 1 megabyte equal to 1,000 kilobytes, but every kilobyte equal to 1,000 bytes. So therefore, 1,000 times 1,000 bytes. 1 megabyte equal to 1,000 times 1,000 bytes, which is 1 million. So 1 million bytes is what 1 megabyte is. And we know that every byte is good for one character, to store one character. So how many characters can be stored in 1 megabyte?
1 million.
1 million characters. 1 million characters can be stored in 1 megabyte. Now, a gigabyte is 1,000 megabyte, and then terabyte is 1,000 gigabytes. So everything is 1,000 here to make things easy. So, I don't have the terabyte here because at the time we wrote this, terabyte was not common, but now terabyte is common. So 1 terabyte is 1,000 gigabytes. So here's my question, warm-up exercise 2. If a storage media has 1.2 megabyte of memory, then how many characters can be stored in it? You have to give me a whole number as answer. Don't give me a decimal number. How many characters?
1,200,000.
1,200,000. Very good. Because 1.2 megabyte times 1 million is same as 1,200,000. For a question like this, your answer has to be whole number. There are questions like this in your homework. Please provide whole number answer only. Okay, so that finishes this portion of the 1.2. That doesn't finish 1.2. It's a portion of 1.2 that I usually teach in this lecture 2, but we are able to proceed to next lecture, so we are going to do that. So this is basically continuation of 1.2. Data representation in the memory. Now, storing numbers, numeric data in the computer memory. Now, like I explained earlier, the alphabets and symbols are all coded using 8 bits or 1 byte, 8 bits or 8 zeros and ones. So therefore, they all need 1 byte of memory to store. each one. But the numbers can be bigger than 1 byte long. So therefore, for numbers, more than 1 byte can be allocated. The programmer will decide how many bytes will be needed. And you'll have to write your code accordingly, write your program accordingly. So we need to understand exactly how these numbers will be stored in the memory. So if your number is small enough, then it will fit in 2 bytes. If it is bigger than 2 bytes long, bigger than 1 byte long, then you can allocate 2 bytes. So I'm going to look at a number that is bigger than 1 byte long. So 1279. If I convert this number to binary code, when I store any number in the memory, it's going to be converted to binary code. Well, the machine, well, we'll understand who converts, who does the conversion. We'll understand that later. But when you store a number by writing a program, writing a statement in the program, or in any other way, if you store a number in the memory, the number will be first converted to binary code, and then it'll be stored in the memory. It'll choose, you'll have to allocate enough memory. So if you look at 1279, the binary code is this. And as you can see, it has 11 bits. So obviously it doesn't fit in 1 byte. So you have to allow 2 bytes. If you allow 2 bytes, exactly how it'll be stored, the latter part of the code, this last 8 bits will be stored in the second byte, the latter byte. The first 3, there are only 3, so you can only give an entire byte. You cannot have portion of a byte. So therefore, you had to allow second byte to store this, and second byte is going to be 8-bit long. So you had to pad it with zeros in the front. Adding zeros to the front doesn't change the value of the number. If you add zeros to the back, it changes the value of the number. So zeros are added to the front to make it 8-bit long, and that's how we are storing that part in here in the first byte. Latter part goes into the second byte, front part goes into the first byte. 2 bytes will be used. If the number fits in 1 byte, then that's all you need, 1 byte. So let me ask you a question now. Can you see that if I change this number right now corresponds to 1279, right? And if I change one of these zeros to 1, then we are adding a power of 2 to the whole value. Can you see that the number will be larger? Right? Number will get larger. If I change another 0 to 1, the number will get even larger. Agree with that?
Yeah.
Okay, then let me ask you this question. What is the binary code of the largest number that fits in 2 bytes of memory? Binary code of the largest number that fits in 2 bytes of memory. Anybody?
3.
3?
In the first 2?
No, I'm asking for the, see, this code here, what you see here is the binary code of 1279, right?
Mm.
But that's not going to be the largest number that fits in this 2 byte, because every 0 here, if I change it to 1, the number will be larger. If I change this to 1, number will be even larger. So what is the binary code of the largest number that fits in 2 bytes?
It'll be all ones.
All ones, exactly. That's the answer what I needed. So there will be 16 ones in the binary code of the number, the largest number that fits in the 2 bytes. Everybody agree with that? Okay, now if I wanted to convert that number to decimal number, then I know that this one corresponds to 2 to the 0, the next one corresponds to 2 to the 1. So I have to write this expression and simplify. Let's actually do that for 1 byte of memory first. So if I have 1 byte of memory, the largest number that fits in 1 byte will be the number that has 8 ones. Okay, then this last, trying to convert it to decimal form now. This last one corresponds to 2 to the 0. Next one is 2 to the 1, dot, dot, dot. What is the power for this, for the first digit? 2 to the power what?
7.
2 to the power what again?
To the 7th.
7, yes, 7 is right. There are 8 bits. Since the powers are starting at 0 here, it will go up to 7. So this, if you add it in the calculator, add 2 to the 0, 2 to the 1, all those manually, you'll get 2 to the 255. But manual calculation is difficult. Now, for this, it's not too bad, but you're going to have to do this for 2 bytes, 3 bytes, 4 bytes, any number of bytes. So I'm going to explain a formula. The formula is 2 to the 0 plus 2 to the 1 plus 2 to the 2, going all the way to 2 to the n. The sum of this will be equal to 2 to the power n plus 1 minus 1. Okay, that's the formula. It's there in your book. It's there in this slide coming up. That formula is useful whenever you need to calculate the largest number that fits in the memory. So this expression 2 to the 0, 2 to the 1, all the way to 2 to the 7, the value of that sum is equal to 2 to the power. Since it ends at 2 to the 7, the sum will be, see, if it ends at n, you have n plus 1. So 2 to the power, 7 plus 1 is 8. 2 to the 8 minus 1. That's the value of that sum. That entire series is equal to 2 to the 8 minus 1. If you calculate 2 to the 8 in your calculator, it will be 256. So 256 minus 1 is 255. That's the largest number that fits in 1 byte. Okay, going over to the 2 bytes, this picture starts at 2 to the 0, goes to 2 to the 1. And if you keep going, this 1 at the front will correspond to 2 to the power what?
7 as well.
Power.
No, here
16th power.
15, right? See, this is the ASCII code of the binary code of one number. So the last one corresponds to 2 to the 0. This one corresponds to 2 to the 7. This corresponds to 2 to the 8. Understand? 2 to the 9, all the way to 2 to the 15. 15 is the power. This whole thing is one number. This entire 16, 1 correspond to one number. So that one number is this. And then you have to compute the value of that expression to answer the question of what is the largest number that fits in 2 bytes. That's one of your homework questions. So I'm going to leave it at that and let you proceed from there. So here is the formula again, 2 to the 0, 2 to the 1, all those, that series adds up to 2 to the n plus 1 minus 1. You're going to have to remember that formula. Okay, so warm-up exercise, what is the largest number that can be stored in 4 bytes of memory? All right, let's work on that. One number that takes up 4 bytes of memory, what will be that number? What is the largest number that fits in 4 bytes? Just a question. All right, so I'm going to, it's a question normally answered by the students, but I'm going to explain that. Here's the first byte. Okay, 4 bytes. So the largest number that fits in here will have ones everywhere, right? Ones everywhere. Okay, so that means let's figure out the powers. 2 to the 0 plus 2 to the 1, the decimal equivalent of that number. Go all the way to 2 to the power what?
Is it 31?
31 is correct. There are 32 bits here. So the largest exponent will be 31. So the value of this entire expression will be equal to 2 to the power what?
32
Thir-
minus 1?
32 minus 1, right. Subtract 1 from the whole thing. Calculate to the 32 and subtract 1 from the whole thing. Now, I'm going to, yeah, I have the calculated number on my keyboard. 2 to the 32 is 4,294,967,276. Subtract 5, the last digit changes from 276 to 275. So this is the largest number that fits in 4 byte of memory. That's also, it's there in your book, but I have a wrong number there. I don't remember what the mistake was. And so the corrections, that's why I mentioned to you that you have the correction document posted on the blackboard. And when you get your copy of the book, you need to make all those corrections by hand on that book. Otherwise, you'll be working with wrong numbers. 290, not 270, 290, 295. All right, anyway, that is the largest number that fits in 1 byte of memory. That's huge. And normally, when you, after you start learning to program, you will realize that the largest, when you declare, when you ask the system to store a number, ask for memory to store a number, it'll give you 4 bytes for numbers because it wants to allow the largest, very large number. So standard memory allocated for numbers is 4 byte by the system. Now we'll learn more details about that after we start programming. We are still at the foundation. We haven't started programming yet. Now we need to understand one more thing, the other coding systems. Now we talked about decimal coding system, which is what we use. We normally use that system. Then the binary coding system became necessary because of the computers. Computers can only represent 2 different things. So therefore, if you convert the numbers to binary code, then all the numbers are represented by 2 things, zeros and ones. And that is necessary for the computer. That's why binary coding is necessary. And using other bases, we didn't have any use for them before the computers came along. So base 2 became useful after the computers were invented. Also, base 8 and 16 became useful in advanced computer programming. So we're going to have to learn base 8 and base 16, but you will not be using those coding systems in this course. But I have to teach you those so that you'll be ready for more advanced computer classes. So you're going to have to understand base 8. When you use base 8, the coding system is called octal coding system. And when you use base 16, it's called hexadecimal coding system. So these 2 coding systems we have to understand next. In octal coding system, you have to express the number as sum of powers of 8. 8 is the base here. So I'm going to show you the work on the side. So let's clear the space. All right, so how do you begin? If you want to convert 459 to octal code, then I had to start at A to the 0, A to the 1, A to the 2. Now, A to the 2 is 64. That's within 459, but A to the 3 is too much. So I stop at A to the 2. And now I had to figure out what numbers to put in front of each. A to the 2 is 64. So basically I had to figure out how many 64s are there. So if you divide 459 by 64 in your calculator, you'll get 7 point something. You ignore the decimal part. That 7 is the number of 64s you have. So 7 goes here. But 7 times 64 is 448. So to make it 459, we need to add these other powers. So that means 8 to the 1 can be included once, because 1 8 can be included, not 2 8s. So if you include by putting a 1 in front of it, then you have 448 plus 8, which is 456. And therefore you need 3 more to make it 459. So 3 times 8 to the 0 will do it. So therefore, the octal code is 713. 713. So that is how you find the octal code. Is there a shortcut method? Yes. Shortcut method would be to divide 459 by 8 repeatedly. 8 goes into 459 how many times? 8 goes into 45 5 times, 59, 7, 3 remainder. Okay, divide by 8 again. 8 goes into 57 7 times. 7 times 8 is 56, so there's a remainder of 1. Okay, so now we have the code right here, 713. From the bottom up, read the remainders, that's your code. So that's the hexadecimal, that's the octal code. Okay, so that's a shortcut method for octal code. Now the hexadecimal coding. Hexadecimal coding means the base will be 16. Base is 16. So that means the numbers, see octal coding system, go back to octal coding system. These coefficients that are the numbers in front of the powers of 8, 7, 1, 3. These numbers can only be less than 8, right? When the base is 8, the coefficient have to be less than 8. They cannot be more than 8. Yeah, I mean, there's no reason to put 8 anywhere. I mean, if this one is going to be an 8, then this whole thing will become 8 to the 2. So that'll change this to 8 instead. So it's not, it's clear that this will not be 8 or more. The numbers, the coefficients will be less than 8. So for any base, the coefficient will be less than 8. Now let's think about the hexadecimal coding. There is a slightly different problem here. So let me explain that on the board. So let's erase the board. Let's say I have a number, and when I try to write the number as sum of powers of 16, let's say I got 16 to the 0 with a 5 in front of it, and 16 to the power 1 with a 11 in front of it. See, any number less than 16 can go there, right? And let's say another one has 16 to the, and then 16 to the 2 is there with the 7 in front of it. Okay, so this is what I found as the expression for the number. Then I will write the code as 7, 11, 5, right? Now there's a problem with that. This double digit makes it a problem, right? You cannot have a double digit. Why? Because someone reading this number can interpret this number as 5 times 16 to the 0 plus 1 times 16 to the 1 plus 1 times 16 to the 2. That's how they will interpret. The 7 represents 7 times 16 to the 3, right? The 1 will be read as 2 different digits. That's going to be a problem. It's actually 11. So how do we say that? We cannot. So therefore, in hexadecimal coding system, we use alphabets along with the numbers. We use, whenever the coefficient is a 10, we use uppercase A in place of that. When it is 11, it's B. 12 is C. 13 is D. And 14 E. 15 will be the largest, right? All coefficients will be less than 16. So therefore, 15 is the largest, so A through F. Those are used in place of those numbers. So this number here, the number that has this expression, will be written as 7 and then what?
Call from 60999137008.
What would be next to 7?
B.
B.
Yeah.
7B5, that's how you write. So hexadecimal codes will have digits and letters mixed. So that's why I'm explaining here 0, 1 through 9, 10, and then 11 through 15 also come up as the coefficients as part of the codes. So therefore, we use A, B, C, D, E, F for the 10 through 15. Okay, so that means here's the number 1279. I'm trying to convert it to hexadecimal code. So I write it as a sum of powers of 16. I have 16 to the 0, 15 times, 16 to the 1, 15 times, 16 to the 2, 4 times. Now calculating this will involve some, if you want to calculate that, you have to use calculator. 16 to the 2 is 256, so you had to figure out how many 256s are there in 1279. Use calculator, you will find 4. And then the rest can be calculated the same way. Anyway, so that's the expression I came up with. So 4 and then 15 and 15, that's the code, hexadecimal code. But 15 is same as F in our coding system. So 4FF is your code. So the code is 4FF, and finding this using this method is kind of difficult. So this quick method of using log division is there the same way. So I can show you that quickly. We have the time. So let me erase the screen. Okay, so if I want to do the 1279, I want to find my hexadecimal code of 1279. So when you do your homework, you can use the shortcut 1279. So I have to divide by 16. So I'm going to show you how you can use your calculator for that. You can do 1279 divided by 16 in your calculator. And I'm getting 79 point, oops. I'm not, yeah, one more time. 1279 divided by 16 equal to, let me write that down, 79.9375. You ignore the decimal part. It means there are 79 16 in there. So just write the 79. Now you need to divide 79 by, you need the remainder, right? So to calculate the remainder, what you do is multiply the 79 and 16. 79 times 16 is 1264. Take it away from 1279. Minus 1279. 15. So remainder is 15. So to calculate the remainder, 79 multiplied by 16 should be taken away from 1279. That gives you 15. Okay, next step is to divide 79 by 15. So 79 divided by 15 equal to 5.266. So that means 5 is our answer. 5. I need to figure out the remainder. To figure out the remainder, 16 times 5 is 80. Oops. Why did I get 5 as answer for 79?
Isn't it 15 times 5?
Wouldn't it be 4? So that you ignore the decimal?
Right. So I'm wondering why the calculator gave me the wrong answer. Hold on. 79 divided by 16 equal to 4.93, not 5. So 4 is the correct number, 4. Now, 16 multiplied by 4, 64, you take away from 79. Take 64 away from 79, 15. So that's your long division. So that's where you stop. 4 is smaller than 16, so you stop there. So the code is 4FF. 4FF. Okay. So that's how you find the hexadecimal code using shortcut method. All right, so that finishes that material. But I'm going to stop here and then proceed with 1.3 in the next class. So next class we'll do section 1. So this I'm not going to add all of these problems of 1.2 to the homework. The homework assignment tells you that you need to do 1 to 14, from 1 to 14 even numbers, but I'm adding one problem to it, 16. So it's actually 1 to 16. Now, when I set up the link on the Turnitin assignment section, like the link you used to turn in the last assignment, when I create the link, I always describe what problem numbers are part of that homework. So it'll tell you more clearly what problems you have to do. So the correct numbers are 1 through 16, not 14. Okay, 16 is added. The remaining problems in the 1.2 will be part of next homework. All right, we'll stop here. Now, anybody has any question?
So this 1.2 homework, that's due next Wednesday, right? Right before class?
Yes.
Okay.
The 1.2 problems 1 through 16 will be due 10 minutes before next class. And the due time will be also mentioned in that link. It'll tell you that due time. So you have to turn it in before that. After the due time, you will not be able to turn in anything. Okay, you have to turn in before that. It's important. The reason there is the deadline has a reason. You have to do it on that at that time. Only then you will be ready for the next class discussion. You are ready to understand the next class discussion only if you do that. So we collect these and grade. You know, the grading is the real hard part of teaching. You know, any instructor, no instructor enjoys the grading part of it. So why do we collect them and grade them? Because that's the only way you will learn. It's because we want to make sure that you learn. And that's why we are collecting and grading. So please do them on time and turn them in on time. Only then you learn and you're ready for the next class, and your progress will be good only if you do them on time. Okay, so turn in this assignment 5 minutes before next class, and you need to type up, but you're only typing up the answers. You're not showing your work. You don't have to. Okay, your answers is all we need. All right, so if you have questions, I can answer them. Otherwise, we are done. So enjoy the rest of the day and enjoy the weekend. I will see you Monday.
Have a good one.
You
Have a
too.
good
Thank
one,
you.
Professor.
Yeah,
Thank
bye-bye.
you, Professor.
I have office hours at 2 o'clock if you have any questions. Bye now.
Professor, I came in late.
I'm sorry, somebody has a question?
I came in late today. Just wanted to check in with
What's
you.
your name?
Gene.
Jean Fair Massey's, right?
Mm-hmm.
Okay, yeah, I got you in late. Try not to be late for classes. It's not a good idea. You won't be able to understand anything if you come late. Okay.
Yeah, sorry about that.
All right. Bye now.
Professor, I just have a doubt.
Yeah.
So the first half of the homework assignment, which is exercise 1.2, that will be due on Monday, and the second half will be due on Wednesday, right?
Right.
Gotcha. All right. Thank you, Professor. Have a good one.
Yeah. Bye-bye.